Okay, folks, hope you've had a try at this question. It's one which covers many of the features of a kind of classic Paper 1B question. Well, you can argue whether there have been enough Paper 1Bs to be a classic, but I'm sure you get my meaning. So, we've got an experiment here where we are looking at analysing a sample of water, and we're determining density, and we're measuring the volume with a measuring cylinder and the mass of the balance. We're asked firstly to identify one way to ensure that the volume is read correctly. The answer I've given here is reading it to the bottom of the meniscus. You should know that when the water is poured in, it will form this curved surface, and that's called the meniscus. We read to the bottom of that, and then we'll make sure that our eye is level with the bottom of the meniscus to make sure that we are reading that accurately, and that's sort of in line with the mark scheme here. The reason I've chosen this one is again to do with the uncertainty calculations. You should be aware now that in every one of your papers, there's always a chance to show your skills with uncertainty calculations, and sometimes these are really nice and sometimes they're horrible, and this one's a pretty okay one. We're being asked to calculate the density and its absolute uncertainty. So we've been given volume here, 10.6, we've given mass, and what we're going to do is do mass over volume is equal to 10.82 over 10.6. I realised I made a mistake when I first did this, and I've gone back and I changed it 1.021. Now that again makes sense. Why? The density of liquids tends to be around about 1 gram per centimetre cubed. We're dealing here with the units grams per centimetres cubed. Okay, or if we're dealing with the alternative units, which are kilograms per metre cubed, we're looking at around about 1,000. Okay, and we'll talk about that later. We need to calculate the density, great, and then the uncertainty. The way we do the absolute uncertainty is quite an involved process. We're doing dividing here. Okay, so delta rho over rho, that's the fractional uncertainty in rho, is equal to delta m over m, fractional uncertainty of mass, and plus the fractional uncertainty in volume. So every time we measure something, if we're multiplying, dividing, we're adding on that fractional uncertainty, and that's important here. We're told the values here, okay, is 0.2 and 0.01 over the respective volume and mass values, and we get a fractional uncertainty of 0.0198, so that's approximately 2%. To get our delta rho, we're then going to multiply that fractional uncertainty by the actual value itself. So we've got, ignore the typo here, I've actually used the right number here, I can explain another time. We're going to take our 0.0198 times the 1.021 to get approximately 0.02. Now notice in the question it does say just calculate the absolute uncertainty. It doesn't say anything about appropriate precision. That comes later. What they then ask you to do is to calculate with a correct precision. So that means delta rho is to one significant figure. So you can present this in any way you want. Okay, there's no worries there. But what you then need to do is turn it into the correct significant figures. We also need to state our answers in kilogram meters to the minus cubed to the minus 3. To do that, that involves a bit of a process. I'll leave that for you to work out. It involves the fact that grams and kilograms are related in this way, and also that centimeters to the minus 3 are related to meters cubed. In end effect, what we end up with a factor is 1,000. So if you, as I said before, we expect densities of fluids to be around about 1 gram per centimetre cubed or 1,000 kilogram per metres cubed. That's multiplying by 1,000. So we're going to take our value 1.021 and multiply by 1,000, 1,021. Look at that lovely writing there. Our uncertainty is also there, so that's 20.2. Okay, and then we're going to turn our 20.2 into one significant figure. 20.2 to one significant figure is going to be 20. Okay, we're then going to reverse engineer our value from 1021 to 1020 because the uncertainty, the leading digit here, has to be the least significant digit here, so everything afterwards becomes insignificant and it's rounded to 0. Okay, so we end up with 1020 plus minus 20. So notice again there, we're turning our significant figures of our delta rho into 1 and then correcting our value of the density accordingly. We're then going to use that value. Okay, so it says here, when the density was measured, the sample was at 35 degrees. The student has a graph which shows the variation of temperature with the density of pure water, with temperature of the density. So we're looking at density on the y-axis and temperature here. And we're being asked to suggest whether this sample is pure. I think it's quite a good question. I mean, it's one that I think a lot of students would sort of maybe struggle with, but once you see the answer, you probably, hopefully, understand what's going on here. First thing to do is to identify that at 35 degrees, we've got a density of around about 994. Okay, so the question is, do these numbers match up? If this water sample is pure, then the density should lie within our uncertainty range. If that's the case, well, let's have a look there. We started with a 1020, 1020, and we have an uncertainty of 20 either side. So we've got 1000 to 1040. Now this value 994 does not lie within that range. It's close, but it's not within that acceptable range, and so therefore our conclusion would be that it is not pure. That's kind of interesting. If you were to do a worse experiment, right? If you were to have a higher range, so for example, I don't know, 100, okay, and the range would be a lot bigger, that 994 would lie inside that. So you would make a different conclusion from the experiment. So this shows the sort of power of our uncertainties on making sure that we're doing good experiments. As I say, it's not the kind of question that comes up all the time. Certainly this uncertainty analysis is, however, using it in this way is hopefully a new skill, and so I hope that that's helped a little bit to see how it is used.